Hello dear students, today we are going to learn about the chemistry of noble gases. So this is a modern periodic table which says 18 columns. The column at the extreme right is known as group 18 or 8b, and the elements belonging to this group are known as noble gases or inert gases. So why they are called inert? Because they do not form chemical bond or chemical compounds with any other elements in the periodic table. So what could be the reason of their inertness? If we look into here, we can see that the common electronic configuration of these noble gases is Ns2 Np6. That means it has a completely filled s orbital as well as a completely filled p orbital. We all know that elements having completely filled valence orbital or valence shell do not want to give or take electrons to form chemical bonds or ions. So this is the main reason of their inertness. However, the term inert is no longer appropriate because in recent years, a few compounds of noble gases have been discovered. If we look into this table, we can see that noble gases constitutes only a minor part of our atmosphere. For example, if we look into here, we can see that helium constitutes only 5.24 into 10 to the power minus 4% of the total volume of the atmosphere. Similarly, the volume percentage of the other noble gases are also very negligible. This is why these gases are also called rare gases. But it is noteworthy that helium constitutes a major component of our sun's atmosphere. These noble gases have various useful applications in our day-to-day life. For example, helium gas is used in lighter than air balloons for weather forecast, etc. Although helium is heavier than hydrogen, it is still lighter than air. Also, it has a very distinct advantage over hydrogen, that is, it is inflammable unlike hydrogen. Helium is also not soluble in water or in our blood under pressure. This is why 80% mixture of helium and oxygen is used in the cylinders that is used for deep sea diving. So what will happen if we use nitrogen gas or normal air instead of helium? Nitrogen gas gets dissolved in our blood under pressure, and this can give rise to a disease called Coulson disease. The temperature of liquid helium is 4 Kelvin. This is why liquid helium is used to maintain cryogenic temperature for different chemical reactions. Liquid helium is also used to maintain the optimum temperature of the electromagnet that is used in NMR machines. Helium gas is also used to maintain the inert atmosphere that is required for various metallurgical processes. Neon gas has a very interesting property. Neon gives a orange-yellow colored hue if we apply high voltage under very low pressure. Also, if we mix neon with any other gases, we get different colored glows. This property of neon is used to make neon glow tubes or neon lights. Argon gas is used to maintain inert atmosphere that is required for various laboratory reactions. It is also used in the dry boxes that are used to store hygroscopic compounds that are air or moisture sensitive. Argon, krypton and xenon gases are used to fill the filament incandescent light bulbs. So let us now learn about the compounds of noble gases. So earliest known compounds of noble gases are their hydrates and chelates. Hydrates compounds are nothing but aqua complexes of noble gases. These compounds are formed by the heavier noble gases. Why? Because heavier noble gases are larger in volumes. That means they are highly polarizable. So if we place these noble gases in the vicinity of a molecule having a permanent dipole moment such as water, an induced dipole moment forms in these gases. This induced dipole interaction is the main reason of formation of this type of compounds. Kletsets compounds are basically host-guest compounds. The host forms a three-dimensional network having some cavities, and the guest molecule occupies this cavity. So let us look into this following example. This molecule is called quinol. If we allow to crystallize a aqueous solution of quinol in presence of a novel gas, for example argon, then quinol forms a three-dimensional network structure by virtue of which hydrogen bonding having cavities of 4 Armstrong diameter. So argon molecules get straight into these cavities and cannot come out afterwards. Argon, krypton and xenon forms Kletset compounds with quinol because their sizes matches with this cavity size. But helium and neon, due to their small size, cannot form Kletset compounds with quinol. However, if we use host molecules that gives appropriate size of cavity, then helium and neon gases can also form Kletset compounds. So these are some recent examples of hydrates and Kletset compounds of various novel gases. So hydrates and Kletset compounds are not real compounds of novel gases because they do not involve any formation of any actual chemical bond. So the first real example of novel gas compound was not discovered until 1962. In 1962, a scientist from the University of British Columbia named Neil Bartlett was studying the reaction of gaseous oxygen and platinum hexafluoride. So he found that the final compound of this reaction consists of O2 plus cation and PTF6 minus anion. That means PTF6 can oxidize O2, or that means molecular oxygen, to its cation O2 plus. So let us look into this following table. Here we can see that gaseous oxygen or molecular oxygen has almost similar ionization energy to xenon. So if PTF6 can oxidize O2 to O2 plus, it should also oxidize xenon to Xc plus cation. So he studied the reaction of gaseous xenon and gaseous platinum hexafluoride under the same condition as the previous reaction. Here he found an orange-yellow colored final compound which he initially thought of consisting of Xc plus cation and PTF6 minus anion. However, in later stages, it was confirmed that this compound consists of XcF plus cation and PTF5 minus anion. Nonetheless, this example is very important because it is the first example of novel gas compound that involves an actual chemical bond. So, under which condition these novel gases can form compounds? So, let us look into this graph. This is a graph of ionization energy plotted against their atomic numbers. So, if we look closely here, we can see that krypton and xenon gases have ionization energy comparable to the elements such as nitrogen and oxygen. So, there is a high chance that krypton and xenon gases can form chemical compounds. So, to compensate their high ionization energy, elements forming compounds with these novel gases should be electronegative enough. That means it should have a very high electronegativity. So, what are those elements? They are mainly oxygen and fluorine because they are the most electronegative elements in our periodic table. In fact, xenon gas can form a number of molecules with fluorine and oxygens, which are fluorides, oxyfluorides and oxides. And in these compounds, xenon gas have oxidation states of +2, +4, +6 and +8. So let us now understand the synthesis and structure of these xenon fluorides. So xenon forms basically 3 fluorides, that are xenon difluoride, xenon tetrafluoride and xenon hexafluorides. All of these are white colored crystalline compounds. Xenon difluoride has a linear structure, xenon tetrafluoride has a square planar structure, whereas xenon hexafluoride has a distorted octahedral structure. So how these xenon fluorides are synthesized? If we react gaseous xenon with gaseous fluorine at 400 degrees Celsius temperature and 1 atmosphere pressure, and if we take xenon in excess, we get xenon difluoride. Similarly, if we take xenon and fluorine in 1:5 ratio at 600 degrees Celsius temperature and 6 atmosphere pressure, we get xenon tetrafluoride. Similarly, xenon and fluorine reacts at 300 degrees Celsius temperature and 60 atmosphere pressure, which is a very high pressure. At a ratio of xenon is to fluorine at 1:20, we get xenon hexafluoride. So let us try to understand their structure in the light of VSEPI theory. So let us understand the structure of XeF2 first. Xenon in the ground state has an electronic configuration of 5s2 5p6. In the excited state, one of these p electron pairs gets unpaired and one electron gets promoted to a higher 5d orbital. So 6 of these atomic orbitals, that is 1 s orbital, 3 p orbitals and 1 d orbital, hybridize to form 6 sp3d hybrid orbital. The 3 lone pair electrons occupies the 3 equatorial position of a trigonal bipyramidal arrangement, and the 2 axial hybrid orbital has 1 electron each. So these axial orbitals then overlaps with 1 fluorine p orbital to give 1 xenon fluorine single bond. This is how 2 xenon fluorine bond forms, and this molecule has a linear structure. So in the xenon tetrafluoride also, 2 of the p electron pairs get unpaired and 2 electrons get promoted to higher 5d orbital. Here we get 6 sp3d2 hybrid orbitals which are arranged in a octahedral fashion. The lone pairs here occupies the 2 axial positions, and 4 equatorial hybrid orbitals overlaps with 4 fluorine p orbitals to give 4 xenon fluorine bond, and thus this molecule have a square planar structure. Lastly, in xenon hexafluorides, all the p electron pairs gets unpaired and 3 of these p electrons get promoted to a higher 5d orbital. In this case, 7 atomic orbitals, that is 1s, 3p and 3d orbitals, hybridize to give 7 sp3d3 hybrid orbitals. In the lone pair resides in one of these orbitals, and other 6 orbitals overlaps with 6 fluorine p orbital to give a distorted octahedral geometry. So in the next class, we will going to understand the synthesis and structure of oxyfluorides and oxides of xenons, and also we are going to learn the reactivity of these compounds. Thank you.